So we can start now. So good morning everyone, good morning Thomas, I will say Thomas.
Okay.
We are together this morning for your PhD defense. So you have written a PhD report that has been reviewed by 2 reviewers, and now it's time for you to start your defense. So this morning the committee has elected me as a chairman. This is the reason why I start to open this session. So in your PhD committee, we will retrieve your reviewers. I mean Gabriela Hug. So just perhaps put up your hands, Gabriela. Yeah. And then Raphael Kerr.
Hello.
As invited professors, we have Bertrand Cornelius.
Hello.
Pierre Passot. And in your supervision teams, we retrieve also Romain Le Goff and Abin Ben Ahmed. So if you are ready, we can listen to you for about 45 minutes for your defense, and after we will have a meeting for discussions and questions with your PhD committee. So if you are ready, you can start.
Okay. Thank you. If that so first, good morning everyone. If that is okay with every member of the jury, I would like to make my presentation in French.
Thomas?
Yes?
Thomas, there's a bad echo. There's a bad echo. Do you know why?
Peut-être qu'on va retirer ça.
Essaye de t'approcher ton micro, s'il te plaît. On va faire un essai.
Is it? Hello? Is it better now? Okay. So we will continue this way then. Right. So I will start again. So first, thank you for being present in these particular conditions. If that is okay with every member of the jury, I would like to make my present in French for family and friends, and of course for the Q&A session following up. It is to be your convenience, either in French or in English. Donc bonjour à tous, merci d'être venus. J'aimerais vous présenter mes travaux de thèse, qui portent sur les marchés de l'électricité et comment ceux-ci peuvent s'intégrer dans les réseaux électriques actuels. Donc, ma présentation va se décomposer en plusieurs parties. Tout d'abord, une introduction qui va présenter le contexte général dans lequel mes travaux s'insèrent et présenter une formulation standard de ce qu'est un marché pair à pair sur laquelle je vais baser l'ensemble de mes développements suivants. Ensuite, 2 blocs de développement principaux. Donc, un qui va concerner les problèmes d'intégration des contraintes du réseau dans le problème d'un marché pair à pair, et un second qui va être sur la prise en compte des agents incertains dans un tel marché pair à pair. Donc tout d'abord, une première question, c'est qu'est-ce qu'un réseau électrique ? Donc il s'agit bien d'un système composé de lignes et de nœuds sur lesquels des agents se connectent. Sorry, Gabriela, for the French. Should I switch to English? Okay. 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 So for the questions, it will be in English. It will be okay. Don't worry. Yeah. Okay. So what is a power system? So a power system is composed of lines and nodes on which agents will connect. We can see two different levels. So first, a higher power level, where big producers and big consumers can connect, and a lower level, where smaller agents, like households and small buildings, can connect. Following this architecture, the current XG market is composed of two levels too. So first, for the larger producers and consumers, so the larger agents, they participate in a centralized XG market, also sometimes called pool market, in which they make bids and offers. For the lower level, so for the smaller agents, they have to pass through an electricity provider, which in turn will participate in the centralized market. With the new developments in the power systems, so such as the growth of renewables and the development of proactive consumers, such as households with energy management systems, or storage, or electric vehicles, etc. There's a question of how this centralized market can be adapted to better include them in the market decisions. So there are two main approaches that are known in the literature. So first, there's the peer-to-peer approach, so where agents can bilaterally trade with each other. So this approach is decentralized. And the second, so based on communities, in which some local markets can appear, and in which the decision making would be distributed. So my PhD work focused on the peer-to-peer market approach. So first, why? So the main argument is that it's a flexible market structure. So we can assume that it may better include large numbers of prosumers, so proactive agents. And the second point is that having these bilateral trades, it can easily express preferences between different partners. And also here there's a possibility of market islanding. So for example, this could be useful for the system operator if there's some technical issue in the physical network. It could send a signal to the market to isolate some part of the market. But first, there's a list of issues that must be dealt with before a real implementation of the P2P market. So first, can it be actually cleared in a decentralized way? Then there's the question of how a grid constraint can be included in the market decision. Then there's how can stochastic agents can participate in a better way to the market decision. There's also the question of multiple time steps. So, for example, to manage storages. Following up, there's having many communication to negotiate these bilateral trades. There's the question of communication delays and faults that could impact the decision making. What is the best market organization, if there is one? We saw two different markets, so community or peer-to-peer. Which one is the best? It might depend on the situation, maybe a mix of them both, of the two. And finally, for example, what about bounded rationality of some agents? So, for example, as soon as they express preferences. So here, on all these points, my work focused on the four first. Now, I will present a standard formulation of a P2P market, starting from the classical centralized XGC market formulation. So first, a centralized market, electricity market, has to minimize the global cost, which is actually the sum of all production and consumption costs, the consumption and production depending on the sign of the local power, with the constraint, the main constraints of respecting the global power balance, which is actually a balance between production and consumption that must be equal at all times. And each prosumer has some technical limits depending on their production or consumption assets. But the problem here is that the centralized, the power balance constraint avoid us from having a decentralized algorithm to solve it. So only centralized and distributed approaches are possible with this problem formulation. Here, the peer-to-peer market proposes to split the local power into multiple bilateral trades, with which each agent will choose to negotiate with partners. And this will change the global power balance into local power balances on each bilateral trade. So if we make the assumption of convexity of the problem, and that all prosumers are rational and non-anticipative, it is possible to say that the peer-to-peer market is a simple relaxation of the centralized market, so they lead to the same global optimum. Then a peer-to-peer market, as expressed here, can allow the expression of preferences, such as here, as simply as a coefficient in front of each bilateral trade. But now comes the question to: is it possible to solve this peer-to-peer market in a decentralized way? So here, based on ADMM, on the consensus form of ADMM, the negotiation mechanism can go as follows. So here, focusing on a particular prosumer N. So after initializing its variables, the prosumer can optimize, can make a local optimization of its assets and propose what bilateral trades it would wish to make with its partners. And it will transmit each proposition to its partners, and its partners will forward him the counter propositions, based on which he will be able to update the trading price based on the difference of the proposition and counter proposition. Based on these differences, the prosumer can also estimate the local disagreement, so which is the local residual, then broadcast to all prosumers, which will also broadcast to all prosumers, so that every prosumer can answer this question: does the market, the peer-to-peer market, reached? Did the peer-to-peer market reach an equilibrium? So if yes, so if all peers agree on a bilateral trade, then the process stops. Otherwise, the process reiterates until convergence. So here we can test this negotiation mechanism on a test case. So here it's based on the IEEE 39 bus system, test system, so on which 4 administrative zones have been included, and here all consumers have been changed to being flexible, so that they can have local optimizations too. So here, after several iterations of negotiation, here are the resulting trades. So it is possible to see that many trades happen cross zones, so the red lines here, and a few happens within each zone, so in a green line. the issue here is that if we do a power flow on these bilateral trades, we can here see that one line is congested. So the line between bus 16 and bus 19, which is within a zone. So here it is possible to clear the peer-to-peer market in a decentralized way, but we can see that there are some issues that with respect to grid constraints. And also here, the formulation that's presented also only include deterministic agents, prosumers. So the next part will focus on how grid constraint can be accounted in the peer-to-peer market decision making. First, so two approaches, main approaches will be proposed. So first, one endogenous, which will include directly the grid constraints in the problem formulation. And then the second proposition is the exogenous form of peer-to-peer market, which will rather allocate operation costs to each prosumers in hope that the grid constraints will be respected. Then both approaches will be compared. So first, a centralized market integrating some grid constraints is called optimal power flow. So it's based on, starting from the centralized market, to which grid constraints are directly included as a constraint. But here also the global power balance is already taken care of by the grid constraints through the power flows equations. So here to include the grid constraints in the peer-to-peer market, we could think of the same approach. So directly including them in the problem formulation. But here, as grid constraint can have losses in the lines, it is we have to take into account to add one agent participating in the peer-to-peer market to provide for losses, so to compensate losses happening in the grid constraint, in the power flows. So here, if we used a standard ADMM approach, only distributed mechanism could be reached to solve this problem. But based on if we take the consensus form of ADMM, it is possible to obtain a decentralized mechanism. So here, if we start from the peer-to-peer market, the standard form of the peer-to-peer market I presented just before, here we can we can involve the system operator in the decision making. The system operator will first make an optimal power flow of what feasible power injections, what are the feasible power injections on his network. And then the system operator can estimate the power losses in his network and update network charges. Then the system operator can send to each prosumer what are the validated feasible, so what are the validated power injections, so which one are feasible, and the prosumers will answer back the system operator with what power injections they would like to carry on the power system. After that, agents would change slightly their local decision making, as they will also update locally the network charges they will have to carry. And here, the local optimization will not only aim at consensus with the bilateral partners, but also at consensus with the feasible power injections, so with the power injection validated by the system operator. So a few remarks here. So here the feasible injections provided by the system operator can be viewed as a shared memory, so sent to each prosumers. This also This helps with the conception of using asynchronous communications from the system operator to the market agents. And here it is possible to say that grid constraints are validated as since the system operator is always included in the loop as to what is feasible or not. So here we can carry the simulations on the same test case as previously. We will, if we compare the results of the endogenous approach, both distributed and decentralized, we can compare the results to a reference algorithm. So here it's MatPower. We can observe in this graph plotting the active power injections for each prosumer. We can observe that they reach the same power injections as the reference algorithm, which tells us that we satisfy the grid constraints and also that we reach the same global optimum. But here the issue is that since the system operator has to be included in the loop at each iteration, it requires a stronger involvement for the system operators, which might later slower the decision making. The second approach, the exogenous approach, takes the priority of the point of view of allocating the operation costs that the system operator faces. So these costs can range from operation costs, such as congestion or supervision of the monitoring of the power flows. But it can also be maintenance and investments on each physical elements of the power system. So in the peer-to-peer market formulation, these grid-related costs can be allocated in the decentralized way, such as follows. So here it would be a network charge applied on each bilateral partner, and the prosumers will have to optimize locally, so their own assets, taking into account that they also have additional costs, which are the network charges. So the advantage here of this approach is that based on the standard peer-to-peer clearing mechanism, we only have to include the system operator before the decision making, before the negotiation process, as the system operator only has to provide the network charges to all prosumers beforehand. So here it would lead to a lesser involvement of the system operator in the decision making, as network charges are given a priori. But here it is not possible to guarantee that grid constraint will be validated, as network charges are given before the decision making. So in my PhD thesis, I proposed three approaches to allocate these exogenous network charges. So first, there's a unitary approach, so where all trades face the same network charge, whichever partners are involved. The second approach here is to focus, so to individualize each network charges based on the electrical distance the partnership will have to carry. And a third approach is based on zones. So here the bilateral trade will be impacted depending on the number of zones they would have to cross between the agents. So we can again test these three approaches on the same test case as before, as previously. So we will compare the results to the case where no grid constraints are taken into account, and we will compare the three approaches of unique electrical distance based and zonal based. And here I will increase the unitary, so the unit fee, and see what happens. So at the first increment of a unit fee, we can see here already two main behaviors. So the unique approach doesn't change the way agents make their partnership, as the unit fee doesn't tweak the different traits, while the two others inside favor some partnerships, so usually closer partnerships or partnerships which are within the same zone. And we can continue to increase this unit fee. So at the next increase, we already have a situation for the electrical distance approach, where there are no longer no congestion in the power system, while the two other approaches still has the congestions within it. So we can continue this until all cases are congestion free. And here are the final situations. So these are the ideal unit fees, depending on which allocation approach we have. So if we take the example of the zonal approach, we can plot the line rates depending on the unit fee and see what happens. So here, for example, for the zonal case, since the congestion happened within a zone, it's less efficient than we could thought at first, which here ask the question of how zones can be designed, because here in this test case it's only administrative zones, so maybe the system operator could have some optimization to have better zoning design. Here, if we take the maximum and average line rates for each allocation approach, we can compare them, and in this graph we can see that, for example, the electrical distance approach provide faster results in reducing the level of intensity in the power system. And these network charges are also used by the system operator to collect money to cover his operation costs. And here again, for example, here the electrical distance approach shows have a lower impact on the market, on the standard market. So based on this graph, we could say that as defined here, the electrical distance seems to be the most effective approach. But here, for all allocation approaches, this graph allows a simple tool, provide a simple tool for the system operator to decide on which unit fee it will send to all agents. So if the system operator wants to collect a certain amount of money, he would look at the lower graph, and if it wants to guarantee a certain level of line rate, it would rather look at the upper part of this figure. So a few remarks are possible. So first, the decentralized, the proposed allocations are decentralized, and they allow they do allow a reduction of congestions in the power system. And a simple tool has been provided for the system operator to decide on which unit fee he has to send to the agents on this particular test system. However, as we could have seen when we increased the unit fee, this exogenous approach cannot guarantee the grid constraints, that their grid constraints are not violated, as they are as network charges are provided before the market decision making. So now we can compare the two main methods, so the endogenous peer-to-peer market and the exogenous peer-to-peer market. So first, we can, so based on the reference of when no grid constraints are taken into account in the peer-to-peer market, we can look at how the bilateral trades are impacted by the different methods and approaches. So if we look at the exogenous approach, we can see here that it has a great influence on the total amount of bilateral trades that are carried in the peer-to-peer market, especially for the unique and zonal approaches. So this is to have no congestion in the power system, right? And for the same result, so no congestion in the power system, the endogenous peer-to-peer, the endogenous approach has much less impact on the volume that are traded between prosumers. So here, yes, both approaches allows to have a congestion-free network, but here the endogenous approach seems to have a better efficiency. It is possible in this table. So here on the right column, that it is possible to see that the zonal exogenous approach allows to have no trades no flows between zones. So we could either the same. So which is important to be able to isolate market zones. So we could ask whether the endogenous approach can do the same. So yes, it would be transparent for the peer-to-peer agents, as here the system operator would only have to suppress the lines that are connecting, for example, here zone 2 and with the rest of the power system, and the endogenous clearing mechanism will operate as presented before without any change. So here both approaches allow to isolate zones, but comes also the question of computation performances. So how long it would take to reach a consensus between all peers. So here, if we compare to the reference case without accounted with constraints, the exogenous approach seems to reach a to reach a consensus within the same order of magnitude of time negotiation time. However, the endogenous approach requires much longer to reach a consensus, as here, as we can see on the right column, as here the system operator will have to be present at each iteration to carry its own optimal power flow, which will slow the decision making of the endogenous approach. So here, based on this table, we could say that the exogenous approach is better computation-wise. So to make a synthesis on what has been presented until now. So first, the peer-to-peer market is a relaxation of the centralized market, and it leads to the same global optimum. It can be cleared in a decentralized way, and but however, the grid constraints cannot be guaranteed, and it doesn't include stochastic prosumers. In this part, I presented two main approaches, two main methods to include the grid constraints in the peer-to-peer market decisions. So first, an endogenous, an endogenous approach, which includes directly grid constraints in the problem formulation, but it requires a stronger involvement of the system operator. And the second approach, the exogenous approach, rather doesn't include grid constraints, but rather allocate grid-related costs. So here, in this within the remarks made on the standard peer-to-peer market, we can say that we have dealt with the problem of grid constraints violation, and we will now focus on how we can include stochastic prosumers in the decision in the peer-to-peer market. So I will start from the centralized form, a centralized approach to include stochastic prosumers in the form of a reserve market, and we'll go to the formulation of peer-to-peer reserve market. Then I will propose two methods to allocate uncertainty between market agents, and finally present some simulation results. So we have to remember here that historically we already had some stochasticity in the electricity market, as for example in households we couldn't predict exactly when someone would plug something in a wall. So, but however, as decisions were taken at the upper level, at a higher power level, so at the transmission network level, it was possible to suppose that each distribution network was deterministic, and to compensate for eventual forecast errors, a reserve market has been put in place. However, the increase of renewables is challenging this two-step approach. So one based on one energy market and one reserve market, as this increase of stochasticity in the market highlights some optimalities of this two-step approach. So here are three main methods to solve stochastic problems. So the first one is the two-stage stochastic programming, but this method only has centralized, to my knowledge, only has centralized algorithms to solve this kind of problem. The second approach is scenario-based, but here, as we have many bilateral trades, it wouldn't be tractable in communication-wise. The third method is the change constraint optimization. However, there are no theoretical equivalent between the centralized and decentralized form of change constraint optimization. But some approximations exist, and I will base my work on these approximations. So here, if we want to include centralized reserves in the peer-to-peer energy market, we would have to take into account that each prosumer can provide a certain amount of local reserves that would be gathered and aggregated at the global level, and it would be then possible to estimate whether there are enough global reserves to compensate for the global forecast errors. This up to a certain global confidence level. For example, if we take 95%, it would mean that the global reserves that we have allow to compensate for forecast errors in 95% of the cases. But here, this last constraint avoids us from having a decentralized resolution. Only a centralized or distribution algorithm could be used on this formulation. So we propose here to not only have a peer-to-peer market on energy, but also to have a peer-to-peer market on reserves. So for this, we would change the change constraints from global to local change constraints on each stochastic prosumer. Here, the stochastic prosumers would have bilateral reserve trades, and they would be able to buy some reserves from their partners. And here we would have again a reciprocity constraint between bilateral reserve partnerships. So basically, there are as much sold reserves as there are bought. But here, can this problem formulation can be solved in the decentralized manner? Yes. It's based on the standard peer-to-peer clearing mechanism. They would only have the inclusion of a market operator, which would provide local confidence level, which stochastic prosumers would have to satisfy. And these local confidence levels will have to be provided before the start of the negotiation process. So here comes the question of how the market operator can estimate the local confidence levels. So two main approaches. The first one is the relative way. So here the market operator would directly allocate portions of the global confidence level into to each a certain agent, while the second approach, the absolute approach, here whether look at the global amount of reserves that satisfy the global confidence, and the market operator would split global reserves into each uncertain agent. So, since there are proportions, a certain parameter allows to design these approaches. This parameter could be either obtained through a ratio based on power forecasts or quality of the power forecast. It could also be defined in a robust way. So here with the unitary coefficient. In the following simulation results, 4 configurations are tested. So each of the 3 allocation factor will be tested for the relative approach, while the absolute approach will only be tested with the parameter based on quality of forecasts. A few remarks are possible. So first, here to obtain this formulation, no hypothesis assumptions have been made on the correlations between stochastic prosumers. But to simplify the estimate of local confidence level, we can assume that stochastic agents are independent. We can also assume that all stochastic prosumers have the same distribution form, so it would be Gaussian in the case, or to have a global distribution, a non-global distribution form Gaussian. We could also take the assumption of large numbers if we have enough certain agents in the market. So here the simulation results will be carried on a second test case, as there is a need to include forecast series. So here the test case is based on the IEEE 14 bus system, on which 5 stochastic agents have been added. Each stochastic agent has a global distribution form, and we will change the the position of the expected power to see what are the effects on the peer-to-peer market decisions. So here, if we first to look at the reliability of these decentralized approaches, we could plot the global confidence level that is actually reached at the end of the negotiation process for each of the approaches. So here we can see that the two approaches in the middle of the figure does not allow does not provide enough reserves to compensate for the forecast errors, at least in the form that as they were presented here. While the two decentralized approach allocations on the right of the figure shows some promising results, but they have some weakness as there's a tail of distribution at the bottom. So if we plot the same graph but with the global power forecast on the x-axis, we could see that the two approaches which showed promising results are actually have good results at higher uncertain power, but show weaknesses only at lower uncertain power. So here it means that some improvements can be made in the decentralized allocation, especially at lower expected power. Also, on the optimality of the decentralized approaches, so here compared in a relative way to the centralized mechanism, we can see that the two methods on the left show better economic results, which is understandable as they didn't provided enough reserves, while the two approaches on the right showed to provide mostly to provide enough reserves, which implies that they have a closer economic result to the centralized approach. And actually, for example, for the 95% global confidence level, here the two approaches on the right have optimality gap with the centralized approach of 5 to 6%. So these two approaches are promising. So to synthesize on the allocation of reserves in the decentralized way. So yes, the proposed peer-to-peer energy and reserve market can be cleared in the decentralized way. Also, this formulation was compatible with the expression of preferences, both on energy trades and reserve trades. But here, the optimality of this market highly depends on the definition of local confidence levels. Two main approaches have been proposed to define these local confidence levels. So first, a relative and absolute approach, and these two approaches could be parameterized with an uncertainty allocation factor. The thesis configurations are promising, but needs improvements, especially at lower global forecast powers. To conclude on this presentation, so first, peer-to-peer markets are a relaxation of the centralized electricity market formulation, and they reach the same global optimum. Peer-to-peer markets allow the expression of preferences, and it can be cleared in the decentralized manner. But in its standard form, the peer-to-peer market cannot guarantee grid constraints and can neither account for a certain agent. In the second section, second part of my presentation, I proposed two main approaches to include grid constraints in the peer-to-peer market. So the first one, endogenous peer-to-peer market, included directly grid constraints in the problem formulation, but it required a stronger involvement of the power system. And the second approach, Exogenous, whether looked at allocating in a decentralized way grid-related costs for each bilateral trade. And the second main part of my presentation focused on how to include stochastic prosumers in the peer-to-peer market. A peer-to-peer energy and reserve market has been proposed, and it was compatible with preferences on reserves and energy and reserves, but the optimality depended on the local confidence levels and how they were provided and they were estimated. Two approaches were proposed to estimate them, relative and absolute approach. They could be parameterized with a coefficient, with an allocation factor, which and the thesis configurations showed promising results, but still need improvements before real implementations. About the future work, so two main directions are possible. So first, the improvement of what has been proposed until now. So, for example, on the grid constraints, we could think on a mix of the two approaches, of exogenous and endogenous approaches, to still guarantee grid constraints, but be lighter on the system operator side. For the inclusion of stochastic prosumers in the peer-to-peer market, it could be investigated the case when stochastic prosumers are correlated with each other. And then to finally, as future work, all extensions could also be carried, for example, to account for multiple time steps, for example, to manage storage and storages. Also, the influence of the communication network could be estimated on the optimality of the decision making, and also the bounded rationality of the different prosumers could be investigated. Thank you for your attention, and of course I'm available for all your questions.